part 5 of the series on chemical reaction engineering. We're going to talk about elementary reactions today. Chemical reaction can usually be written just with stoichiometric coefficients being correct. They usually don't represent any mechanistic ideas of how the reaction actually occurs. The exception is when we write down an elementary reaction, in which case it is a stoichiometric equation, but it also does reflect the way the reaction actually occurs. That is to say that the events in the reaction correspond to collisions between the reactants on the left to make the products on the right directly with no stable intermediates in between. If you have a reaction written in the form that we've been using as our generic form all the way, this A moles of A plus B moles of B, it goes to C moles of C and D moles of D. If it's elementary, then it automatically, we know, is going to have a forward rate law, which is given by the rate in the forward direction is a rate constant for the forward direction multiplied by the concentration of species A to the stoichiometric coefficient of that species multiplied by, multiplied by the concentration of species B to the stoichiometric coefficient for species B. Sometimes our elementary reactions are reversible. We can tell when they are reversible by looking at the Gibbs free energy for the reaction. If it is not extremely negative, then the reaction will actually be reversible. And in that case, the reaction must have a reverse rate law that's given by reverse rate constant times the concentration of product C to the power of its stoichiometric coefficient C, and the product D to the power of its stoichiometric coefficient D. Okay, so these Kb and Kf, these are backward and forward rate constants respectively. We call them rate constants because apart from non-idealities, these things really do depend only on concentrations. And in fact, they are very similar in their properties to equilibrium constants, except of course that they involve a prefactor that depends on time. We will talk about some of those things a little bit later. But elementary reaction rate constants typically have this very strong Arrhenius temperature dependence. That is embodied by this expression where you write that the forward rate constant is a numerical prefactor with units of inverse time and perhaps also units of concentration to the -1, multiplied by an exponential of a negative activation energy divided by the gas constant times temperature. Okay, so this E sub A parameter is the activation energy. I want to emphasize that the Arrhenius law depicted here is an empiricism. There are many exceptions to this, and exceptions that actually do occur for elementary reactions. An important example is the diffusion-controlled reaction rate constant between species A and B. That has a reaction rate that is approximately, as long as A and B are of comparable size, that is given by 8 times the gas constant times temperature divided by 3 times the fluid viscosity multiplied by the concentration of A times the concentration of B. So the rate constant is this thing in the circled dotted line. It's called the diffusion-controlled rate constant. And what you'll see from this is that as long as the medium in which this reaction is occurring in is not a solid or a glass, then this viscosity does not have an Arrhenius dependence on temperature, and therefore the reaction rate doesn't look like an Arrhenius law at all. Okay, so this is just one example that you can construct for looking at exceptions to the Arrhenius law. So at equilibrium, the forward and backward rates for a reversible elementary reaction have to be equal. That is to say that Rf equals Rb, or written in terms of the concentrations, we have that K forward times the concentration of A times the concentration of B, each raised to their stoichiometric coefficients, must be equal to the backward rate constant times the concentrations of C and D, each raised to their stoichiometric coefficients. So we can take this equation, which is a statement of something called detailed balance or microscopic reversibility, and it implies a relationship between the rate constants and the equilibrium constants. Okay, so recall that our equilibrium constant in terms of concentrations was the product concentrations raised to their stoichiometric coefficients divided by the reactant concentrations raised to their stoichiometric coefficients. So this ratio, we can obtain this ratio also from this equation just by dividing through by A to the A and B to the B, and Kb on both sides of this equation gives us that this ratio of concentrations, this max action law ratio that appears in the expression for the equilibrium constant, is also equal to the ratio of forward and backward rate constants. So this, as I mentioned, this relationship has an important place in a lot of chemical physics. It is the principle of detailed balance, also known as the principle of microscopic reversibility. And in the context of elementary reactions, it's basically a statement that the forward and backward rate constant balance each other. Neither of them really stop at equilibrium. They just begin to occur at the same rate in opposing fashion. So we can find many examples of elementary reactions. One is the dissociation reaction, which we'll see quite a few times in this course. Nitrogen pentoxide going to NO2 plus NO3 has a rate constant that looks like this. This is the Arrhenius approximation to the temperature dependence of that rate constant. Notice that this rate has units of inverse time, so that when I multiply this number time with units of inverse time by the concentration of nitrogen pentoxide, I get a moles per volume per time rate, which is the correct units for describing a rate process that's happening in the volumetric bulk. So the inverse time is all we need for the units to give us something multiplied by concentration. Gives you that volumetric rate constant units. We can also find examples that are isomerization reactions. For example, the Koch-Claisen rearrangement is this reaction here. We can find examples that are nothing more than conformational changes, like the chair-boat interconversion of cyclohexane. There are also bimolecular reactions that can be elementary reactions. An example of this is NO combining with NO3 to make two molecules of NO2. Okay, so this reaction it's bimolecular, and the rate constant should have units of volumes per mole per time, so that when you multiply that by moles per volume and moles per volume, you end up with moles per volume per time on the right. You end up with moles per volume per time for the rate of the chemical reaction. Another common example from your chemistry courses that you may remember as a bimolecular reaction is the Diels-Alder reaction, where these two conjugated diene molecule, the conjugated diene here combines with the olefin and makes a molecule with a ring and a double bond. The trimolecular elementary reactions are much more rare. They include things that involve water bridges, for example, where you have ligands attached to a metal and an oxo group. You can bring in peroxide, and you could write this stoichiometrically without the water here. Notice that the water is looks like it's just a innocent spectator here. So certainly stoichiometrically, this looks like the peroxide just combines with this ring and gives you this, combines with this metal oxo group and gives you this hydroxyl and peroxo groups on the metal atom. But actually the reaction turns out to be proportional to water concentration. This is one that we've worked on with Professor Susanna Scott. And the water is actually an integral part of the transition state here. And so it would be right then to write it as part of the elementary reaction so that you can actually see that the reaction really doesn't occur unless there's water in the environment. You can also find, and there's a picture of that transition state where the water is helping to transfer the hydrogen from one site to the other. There are also examples where you have association reactions at low pressure that involve a third seemingly innocent bystander that is actually doing something important in the mechanism. So an example here is the hydrogen radical plus a bromine radical would like to combine to make hydrogen bromide. but they can't do so if there's not another collision partner around. The reason is that if you take two atoms that have enough energy to stick to each other, then once they find each other and stick, if nobody hits them and takes away some of their energy, they will eventually come unstuck, because the same path that brought them into a position where they could stick to each other, they still have enough energy to recross right back through that path until some argon atom or something like some other inert comes by, collides with them, and takes away some of that excited vibrational energy of this early product complex HBr. So this reaction actually does have a third order rate law. It depends on the concentrations of both the reactant, the product, and a collision partner. And it's an example of a rather rare example where an elementary reaction involves a three-body collision. So quite often we will find that even our simple stoichiometric reactions are actually not elementary. In fact, in Helfrich's book, he has the amusing little quote that single-step reactions are usually found in textbooks. But there are quite a few examples of elementary reactions, and they are important in describing the mechanisms of more complex multi-step reactions. What we will do in this course is take our multi-step reaction mechanisms and write them out as a whole long series of elementary reaction events, and then go through and solve for what the overall rate law is in terms of various assumptions that we will have to make about those elementary reactions involved. So a important example is the reaction between hydrogen and bromine gas to make hydrogen bromide. Okay, so this looks like it could be an elementary reaction. You could certainly imagine a case where you arrange the two molecules like this, and then the bonds between hydrogen and bromine begin to break and form new bonds between hydrogen and bromide, and going through a transition state looking something like this to leave you with two hydrogen bromide molecules. The problem is that the rate law would be a rate constant times the concentration of hydrogen times the concentration of bromine. And this is actually not supported by experiments, nor is it supported by quantum mechanics, which would tell you that this transition state is really non-existent. It doesn't correspond to a saddle on the potential energy landscape. And we won't talk very much about that in this course, but it's fun stuff, and if you're interested in it, take a computational chemistry class. So the actual mechanism does involve two elementary steps. You first have a reaction between a bromine radical and a H2 molecule to give you hydrogen bromide plus a hydrogen radical. Now that hydrogen radical turns around and reacts with a bromine molecule to give you another hydrogen bromide plus restoring the bromide radical again. Okay, so if you add these up, you get a net reaction that is indeed the stoichiometric reaction that we proposed initially. That is that hydrogen and bromine in their molecular states directly convert to two molecules of hydrogen bromide. The reaction involves an initiation step where you use, for example, a photon to create the first radicals. And then the reaction ends when the radicals quench each other. That is, when the radicals become appreciably common relative to unreacted H2 and Br2. Then the radicals can start to recombine and either make more product or to restore the hydrogen and bromine concentrations. So a common but not universal feature of reaction rates, in fact, in Davis and Davis, which is the book I'm following for this course, he lists an entire section of these features of reaction rates, these rules that he calls them. But many of those rules have many contradictions. There are many examples where there are sort of counterexamples to those rules. And in fact, I think in most cases, there are so many counterexamples that you might just not want to learn those rules at all. There's one that is very common and almost always is obeyed, and that is that the rate tends to decrease as the reaction proceeds. This can happen either because the reaction is approaching equilibrium or because the reactants are being consumed. And these are, of course, closely related in most cases. An example exception, though, so as with all of these rules, you can find exceptions. The exception in this case is something called autocatalysis, and that is where you have a slow reaction that generates the first products, but then the products catalyze the conversion of additional reactants into products. For example, A goes to B, if that's a slow reaction, followed by a fast reaction where you have A plus B goes to two B molecules. Then the presence of B is effectively helping to convert more of the reactants. And so what happens is that at the beginning the reaction is slow because there's no B around and you have to wait for the slow reaction to generate some. Then after you start to make some B, the reaction starts to go fast, and eventually it will exhaust the supply of A, and the reaction will again get slow. Okay, so this is a very typical behavior of an autocatalytic reaction, and it's an example where the reaction is fastest at a point where it's already gone somewhere close to, somewhere on the way to approaching equilibrium. So we're going to stop here and do some examples in the next one.